So I hear she's still not feeling really well, but she's still willing to give the talk, so I'm very happy to hear that, and we're all curious to learn more about Monoid, so please, go ahead.
Okay, thank you. Yeah, excuse me. So my name is Julie Moronuki, and I am sorry. I was supposed to be here this morning, and is there a strange noise? Can you hear it too? Okay, I'm glad it's not just me. I'm sorry, I was supposed to be here this morning. I've been quite unwell ever since I got to London, which I'm sure is not London's fault. But I'm gonna do the best I can to get through this today, so hopefully it'll go all right. Okay, so yeah, my talk is called A Monoid for All Seasons, which is taken from the play about Sir Thomas More, A Man for All Seasons, if you're familiar with that. There will be some Thomas More quotations throughout the slides. So, this one is made up. All right, so as many of you know, I am one of the co-authors of Haskell Programming from First Principles, which is also known as Haskell Book. And as some of you probably know, but many of you may not, when I started writing Haskell Book, I didn't know any Haskell, and I really hadn't had a math class of any kind since about 1992. And I was convinced that I disliked math. I was a math hater. I was a math phobe. And it was through the process of writing Haskell Book that I started getting interested in math. And so when I started writing Haskell Book, I had never heard the word monoid before. And now I am known on Twitter as Monoid Mary. So because I have developed a great love for what monoids have taught me. So we're going to cover in this some monoids in Haskell, a little bit of historical perspective. Particularly, we're going to start by talking about things that I knew about monoids without knowing the word monoid before I started learning Haskell. And then we're going to go through some abstractions, some mathematical abstractions. All right, so some of you will be, as I said, I didn't have any math classes, and I was a confirmed math phobe, but I had quite a few logic classes because I was a philosophy major. So some of you will be familiar with this very famous syllogism from Aristotle. For a long time, all logic was considered to be Aristotelian logic. People considered that what Aristotle had said about syllogisms was it. He had completely said everything that needed to be said about logic. And his concern was mainly for finding things that would be logically valid. And validity means that if your premises are true, then the truth of your conclusion is guaranteed. So Aristotle had not very many kinds of propositions that he could talk about, basically 4. And these ones, for example, are all considered to be, in Aristotelian logic, universally quantified. It seems strange to think of Socrates as a man as being universally quantified, but for every Socrates, he is a man, right? So this is considered to be a universally quantified proposition. And we can sort of see, intuitively that the conclusion follows from the premises. So in the Middle Ages, then, there developed this system, because people thought that Aristotle had said everything that needed to be said about logic. Not everyone agreed with this, Leibniz, for example. But they developed this system of syllogistic mnemonics in which there were considered to be 256 logically distinct syllogistic patterns. And you could memorize these 256. Not all of those are valid. Some of those are invalid. But you could memorize the 256 syllogistic patterns through this series of mnemonics. And this is not, obviously, 256 of them. But these are people's names, and if you memorize the 256 names and the rules that these encoded, the rules that these were supposed to help you remember, then you would know all of the syllogism patterns that reason could give us. So, for example, the vowels represent the types of propositions, Like I said, in Aristotelian logic, there are 4 types of propositions. And so we have A, E, I, and O. Is that all of them? Yeah, I think so. So those are the 4 types of propositions, and A is for universally quantified propositions. And then the consonants represent different patterns of syllogism and different transformation rules you would have to use to get somebody's argument into the right kind of syllogistic pattern. So you would memorize all of these and memorize what B and R, for example, in Barbara meant, and then you could figure out that this syllogism, for example, is a Barbara syllogism. But this is a very cumbersome way, even if you think Aristotelian logic is all that ever needed to be said about logic. This is a very cumbersome way to memorize and talk about arguments. So, in the 1800s, George Boole came along and wanted to see if he could come up with an arithmetic or algebraic way of reasoning, to make a science of reasoning, he said, and not a mere mnemonic art. So that we would no longer have to memorize syllogistic patterns, but we could use operators that have understood laws and properties, use variables to represent the propositions, symbolize verbal arguments thusly, and then manipulate them algebraically. And by doing that, instead of memorizing syllogistic patterns, we would have an algebra of logic. This is something Leibniz had dreamed of previous to Boole, but Leibniz never completed that project. So we had to wait until about the 1850s or 1860s when Boole did this for us. And then it's been developed significantly since then. All right, so if we look in arithmetic, we have 2 very nice operators available for us, right? Addition and multiplication. These share some properties. They're both binary operations that are associative and commutative. Commutativity is not going to be a big thing throughout the talk because not all monoids are commutative. But they do have to be binary and associative. And sums and products both also have identity values. So we have these operators from arithmetic that we can use to talk about logic in the same way. So for Boole, Boolean logic is a 2-valued system. Every proposition is either true or false. So for Boolean disjunction, we only have the 2 values false and true. Disjunction is like an OR. It can be an inclusive or an exclusive OR, and I'm not going to always keep that distinction clear, I suppose. But the truth table roughly looks like this for an inclusive OR, right? Only when there are 2 false values do we get a result of a false value. And that's analogous to binary addition, because we only have 2 values. So only when there are 2 zeros do we get a 0. Now with binary addition, if we're doing an inclusive OR, an analog to inclusive OR, then we would want the 1 from the 10, right, to correspond to the true in Boolean disjunction. If we're doing an exclusive OR, then we want the 0, right? So exclusive OR would look like this, right? An inclusive OR will look like this. For most of the purposes of this talk, that doesn't matter very much. All right, in conjunction, Boolean AND looks like this. This corresponds a little more nicely to the binary multiplication table. Okay, so we've got these two basic operators. There are some other operators in Boolean logic. There is a not, of course, like a negative in arithmetic. And there is another one for if-then. But these are the basic 2 that we care about, because these are the 2 that are monoids. All right, so sums and products also share a kind of relationship with each other. So there's first the distributive property, in which multiplication distributes over addition. Right, so that's a relationship between the 2 things. And the identity of the 1, the identity of addition, is the annihilator of multiplication, right? So a 0, which is the identity for addition, is the annihilator for multiplication, right? And conveniently, or by design, however you look at it, Boolean operators follow the same, share the same properties and the same relationship with each other. So Boolean conjunction distributes over disjunction in the same way that multiplication distributes over addition. And we have proven it with quick check. So we know this to be true for at least for at least 100 cases, right? All right. So Boolean conjunction and disjunction share the distributive property, and there also is, in some sense, the same annihilator relationship. It's a little odd because with only 2 values, you could also say that true in a disjunction, for example, if we reversed the disjunctive fold R up there, and we use true for identity and we gave it a list of false, we're going to get true, right? So in some sense that annihilates all of our false values. But I think it's still okay. I'm still comfortable calling false the annihilator for Boolean logic because normally I think we want to sort of propagate truth, right? And so giving us a false when everything else is true is more like annihilation than giving us a true when everything else is false. I'm comfortable with that, but it's perhaps not quite as clear as we would like it to be. Okay. All right, and then we also have a correspondence then. Boolean logic and was sort of happening around the same time as set theory and first order logic were sort of starting to take off, right? And so we can also draw these kinds of sets that correspond to Boolean operations. The top we have conjunction, so A and B, and that's in the Boolean world, that is sort of analogous to a set intersection, right? Where the colored space is exactly A and B. And also the space that would be the conjunction of those, the intersection of those 2 sets. And on the bottom here we have disjunction, A or B. Now again, we would have a distinction between an exclusive and an inclusive OR. So an inclusive OR, which would correspond to a disjoint union, not a normal set union, but a disjoint union. Inclusive OR gives us this pattern where C, the colored part, is all of A and B. We'll talk more about disjoint unions in just a minute. The exclusive OR would mean that the space in between A and B, exactly what's colored in the intersection, would be white because we normally want our sets to have unique elements. All right, so then set operations, union and intersection roughly, share many of the same properties as the arithmetic and Boolean operators, right? They're binary associative operations, they are commutative, they have identity elements. The identity of union is the annihilator of intersection, and intersection distributes over union. So they share the same set of properties. Now these were all things that I knew before I ever heard the word monoid. But probably many of you can see where I'm going with this. All right, so let's take a moment to talk about disjoint unions and Cartesian products, because one of the things about set union and set intersection is that they don't correspond very well to our intuitions about sums and products, right? The intersection of 2 sets doesn't really seem like multiplication, and the union of 2 sets doesn't really seem like addition. But if we look instead at the set operations, disjoint union and Cartesian product, those correspond a little bit better to our intuitions about arithmetic. So if we have 2 sets, A and B, and A has London and Tokyo in it, and B has London and New York, then the disjoint union, or tagged union it's sometimes called, of those 2 sets gives us this union here. In a normal union, we would only have 1 instance of London because we want to have uniqueness of elements. But when we tag them, we can say that the London that came from A and the London that came from set B are distinct elements, and we can keep them both together then. And so the cardinality of a disjoint union will be the same as the sum of the cardinalities of the two input sets. And so in that way, it sort of corresponds to our intuitions about addition. The Cartesian product, I probably should have picked sets that had 3 elements each to show that this is more like a product and this is more like a sum. But I think that you can see that. Because, of course, 2 plus 2 and 2 times 2 are the same. Right? 3 would have been better. But the slide wouldn't fit them. So in a Cartesian product, we make ordered pairs of all the elements from the 2 sets. So we get a set of sort of tuples of all of the elements. And that's why it's a product, right? If we had London, Tokyo, Osaka, and London, New York, I don't know, some other city, Paris, then we would have 9 elements in our Cartesian product, right? 9 tuples. So the cardinality of a Cartesian product will be the same as the product of the cardinalities of its 2 input. And so in these ways, we have set operations that do correspond to our intuitions about arithmetic. One thing that interested me when I started learning some things about algebraic data types and the ways that they work is that it's disjoint union and Cartesian product that correspond to sum and product types in Haskell. All right, so there came this moment in writing Haskell book when I was finishing up writing the type classes chapter, which is fairly early in the book. And while it introduces the idea of type classes, a lot of it is about some of the standard type classes like num and ord, right? And then it talks about how there has to be this unique pairing between a type class and a type, right? In the instance, because that's how it looks up what the implementation is, right? So I was finishing up that chapter, which is fairly early in the book, and my co-author had started making some notes and providing some examples for the Monoid chapter. This was really serendipitous because it was really a nice pair of things to be working on. So he sent me some notes. We had this process where he would write a few notes and a little bit of example code because, of course, I was learning Haskell as I was writing. And he would send it to me, and I would start asking questions and making notes of my own. And the questions that I asked and would sort of direct our further writing and expansion and research of the chapter. So he sent me very few notes, but he said, a monoid is a binary associative operation with an identity element. And he explained what that meant, because I'm not a math person. And then he sent me these 3 examples, which I think are 3 very common examples that we use to introduce monoids to new learners of Haskell, right? So we have, let's call these numbers, let's call them integers, okay? Because for some kinds of number, for some types of numbers, addition and multiplication are not associative, which is an unfortunate fact, but so let's call these integers so we don't have to worry about all the different types of numbers. So we have addition, all right. We have multiplication, okay. And then we have list or string concatenation. And these are sort of the 3 things that we always introduce people to monoids with. But these 3 things are unlike each other in some ways, right? So this bothered me. This was bothering me, and many of my questions at first were around this. For me, I can say it's multiplication that doesn't belong here. Why? Because multiplication is a product or a conjunctive operation, right? It is binary and associative, but it's a different kind of implementation than the other 2. Or I could also say that this one is different from the top two, because integers, for example, are a concrete type, and lists are a type constructor, right? And so yes, it's true that these are all binary associative operations that have an identity element, and they all can be represented with the type signature of append, which is A or M to M to M or A to A to A, right? And then they just have different implementations. But as I was writing the type classes chapter, I was writing a lot about how the pairing between a type class and a type should be unique. And it doesn't seem like we have something unique here. It seems like we have integer has two monoids over it. And indeed, as I started learning more about them, I found that there are more conjunctive monoids. That, for example, this is how we do the uniqueness relationship. We wrap bool in a new type wrapper. We call it all because this is the conjunctive one. And this is a conjunctive monoid. Right? It follows the same sort of, it has the same sort of properties that I expect from other instances of products or conjunction. And we can make a monoid for a zip list. There are different ways that you can implement this. This is one, which behaves differently from concatenation because it behaves conjunctively. So here the empty list will, where the empty list is an identity value for concatenation, here it will, if you zip a list of elements with an empty list, you'll get back the empty list, right, and lose whatever was in the other list. So I did find that in Haskell we have plenty of perfectly valid monoids that behave conjunctively, but we tend, as a rule, to make our default ones and think of them in, like with concatenation, we tend to think of the disjunctive ones as being defaults. So I spent a lot of time then thinking about maybe monoids. There are sort of three. There's the default maybe monoid, which is fairly disjunctive. So the default maybe monoid behaves such that if the only time you get a nothing result is when there are two nothings. Otherwise, you will get back whichever just you have, or if you have two justs, you'll get back a just with the two A's appended, right? And you can make, though, a conjunctive maybe monoid. I called mine mabes. You can make a conjunctive one that behaves like Boolean conjunction or a product, where anytime you have a nothing that corresponds to, say, a false or a zero value, right, you'll get back the false or the zero value. This is a valid maybe monoid. I'm not sure it's useful, but it is a valid maybe monoid, and it works. Right? You'll notice that we are relying on the monoid instance for strings, right, to append hello in London up there. But over the maybe type, this is conjunctive. So I noticed that we can have two or more types or varieties of monoid instance for almost every type I can think of. We don't necessarily have them all written in base or available in any libraries that I know of, although somebody's probably written them. We don't necessarily have them all because the things that are in base are the things that somebody thought would be generally useful, right? Or in and so generally speaking, we find the disjunctive ones to be more useful when we're talking about monoids. I think it's because of the kind of annihilation property that conjunction has, where one false value or one nothing value or one left value will kind of short circuit your whole operation and you get nothing back, right? So generally speaking, when we're appending things, that's not the behavior that we want. They're valid monoid implementations, but that's generally not the behavior we want with our monoid instances. So, all right. Before we go on and okay, so we've looked at this pattern of having disjunction and conjunction over a variety of types. Right? We've talked about integers, which have this pattern. We have talked about Booleans, which have the same pattern, except for now our two values are true and false. We have talked about sets, which have intersection and union, or disjoint union and Cartesian product. And then we were just talking about maybes, right? And lists can follow a similar pattern. All right, so I've always liked this quotation because we often find it to be true that what we've come up with is not so much a new idea as some way to restate an old idea. So we have this pattern over and over again, right, with all these different types or sets or however you want to think of these things. And so what we need to talk about them really is an abstraction. Okay, yeah. So the idea of an algebraic structure was new to me, but what a valuable way to talk about things. So an algebraic structure is a set called a carrier or an underlying set, such as integers or Boolean values or sets like maybe, with one or more finitary operations defined on it. I'm not sure what an infinite operation would actually look like, so most of the time the finitary operations are just what we think of as operations. But it means that we take a finite number of arguments, for example 2, like a binary one, that satisfies a list of axioms such as associativity and commutativity. So that's what an algebraic structure is. And a monoid is an algebraic structure. It is a set with a binary associative operation defined over it that has an identity element. Okay, so this is a very useful way to be able to talk about these patterns that we've seen with all these types, right? And as I learned what an algebraic structure was, I started to think of the relationship between types and type classes or type class instances as an analog of algebraic structures, where the type corresponds to the carrier set, and the type class instance corresponds to the operations in the algebraic structure. And in the case of monoid, also then to the identity element, which we'll consider to be an operation. All right, so as I said, when we're talking about type classes and types in Haskell, we have to keep the relationship between them unique. So one way that Haskell does that is by doing these new type wrappers. So all is, a different type than bool, even though its underlying representation is bool. Okay, so then we can have a monoid for all, which is a conjunctive Boolean monoid. And we can then have a separate monoid called any, which is still just a Boolean monoid, but it's the Boolean monoid under disjunction. And since it has a separate name, then we have preserved that unique relationship. Now, it's not the only way that we could do it, and I've been thinking about this for a long time, different ways that we could do it. So one way that Foundation did this for numbers, a Foundation library did this for numbers, split the two type classes. So now there's an additive type class, which has a 0, and then the plus operator, and a multiplicative type class, which has a different identity, and the multiplication operator. Now, as far as I know, Foundation has only done this for numbers, but it could do disjunctive type class and a conjunctive type class and use them for other types, right? Because we've just seen that many types follow this exact same pattern. Another way is to just make a semi-ring type class. And this has actually been done in Haskell too, but I think PureScript actually has this in their base library. And I really like this. So hence why I brought it up. So a semi-ring is just the kind of thing we've been looking at, right? Semirings are algebraic structures in which the set has two monoids defined over it, and the identity of one is an annihilator for the other. And that's a semiring. So all of the types that we've talked about so far are semirings. Haskell's types themselves, the sum types and the product types, also form a semiring. So I think they're also a very useful algebraic structure to be able to talk about. And so I like the approach that PureScript took by just joining these. Now, not all monoids are, not all sets that are monoids are also semirings. So you still need a monoid type class. But I like this because it sort of keeps with our intuition that there's this relationship between addition and multiplication. Okay, so then the question is, can we abstract even further with this and give ourselves a new way to talk about these relationships? Because we've developed this sort of intuition that this relationship between addition and multiplication, conjunction and disjunction, all of these things, right, that this is sort of pervasive, right, that this happens a lot, that we have a lot of cases of this. So, all right, so can we abstract a little further and find a way to talk about what that relationship is? Hang on just a second. Okay, to talk about the way that relationship in even more general terms than we can with an algebraic structure, right? Because with an algebraic structure like monoid, we have a set that has a binary associative operation defined over it, right? But we sort of know that a lot of sets have two of them. So we can talk about the semiring structure, but we really want to talk about what's the general relationship between these things, right? All right, so this is how I started. This is the path, the dark path that has led me to start learning about category theory. For me, it was monoids that did it. All right, and I don't know a lot still about category theory, but monoids were my gateway drug. It was noticing this relationship between monoids and then applicatives, because applicatives are monoidal functors, right? And Haskell's type system that made me think there's really something going on here, right? Something more fundamental than just than any way I've been able to talk about it so far. All right, so we have this notion of a category, which for me, perhaps only because I'm a novice, I'm not sure, sort of corresponds to the idea of an algebraic structure. Except for now we have a class of objects, such as sets, plus a class of arrows or morphisms between the objects. These are often functions, but it's really sort of better to think of them as relationships between the objects, because they don't always correspond with exactly what we think of as a function. Admitting a binary composition of morphisms, so that means that we get function composition, right? For every morphism A to B and then B to C, we can compose them, right? And that's a very nice property to have. And that satisfy a couple of axioms, such as associativity of the composition, so that if we also had another, function that could compose with F and G there, then it would, G, F, and H composing them would be associative. And an identity of objects. So every object in the category has to have an identity, so an arrow or a morphism to itself. All right, so when we talk about monoid then, we've got monoid, the algebraic structure, which is a set with a binary associative operation and identity element. If we talk about a monoidal category, then we've got a category M with a binary associative operation, M and M going to M. and an identity, I. There are a few more things that we need to have a monoidal category, and we're going to just brush them off right now. So one thing that I like about this is that this binary associative operation looks to me like another way to write the type signature of append from the monoid type class. Okay. So these are also not entirely precise. There are some other things that should be in these diagrams for a proper monoidal category, but let's talk about what is here. So in a monoidal category, it's the Cartesian product that is the basic operation that we care about. So this and sum or disjoint union is considered to be the coproduct. It's the dual or the opposite of the product. So we start when we're talking about a monoidal category, we start by talking about products, which are Cartesian products or generalizations of Cartesian products. And their relationships, there's the I, so that's the identity, because we have to have an identity for a monoidal category. Well, we have to have identities on the objects anyway for every category. And then we've got these things. You can see that there's only really one object in this category, right? They're all M's. So all of our morphisms are going just from M to M to M. All the endpoints are the same, which means we get very easy composition. And then the coproduct, we can make the dual of a category by just flipping around all of the arrows. And since this corresponds to the disjoint union, then that's how we can see that there is a very natural, structural, fundamental relationship between sums and products. So all of our intuitions that we've gathered, looking at all of these types and all of the ways that these things behave in Haskell, is at some very abstract and fundamental level real. And that's a very satisfying feeling. Oh dear. All right. Let's go to the empty set for a minute. I seem to be missing a slide. I'm sorry, because I was going to talk about how in Haskell there's understanding monoids can lead you to understand many, many more things about Haskell, right? So folds are monoidal in Haskell. Applicatives are monoidal functors. They're a way of mapping monoidal things together. Monads also are monoids in the category of endofunctors, right? Famously. But their applicatives and monads are, interestingly to me, they are conjunctively monoidal, right? Because they both will short circuit on any nothing or false or left or whatever your sort of empty value is, right? They both will kind of short circuit on that. Applicatives don't have to exactly, and monads do, but they both tend to behave conjunctively. So they've got this kind of error propagating feel to them. Unlike our normal monoid instances, which have this error correcting feel to them, right? They forgive us our errors, whereas applicative and monad punish us for nothings. And alternative is another monoidal type class, right? Alternative is a type class that I use quite a bit for parsing, and this slide was supposed to have some stuff on it about alternative, and I don't know what's happened. But alternative is a monoid over type constructors, and it's a disjunctive monoid, usually, and meaning that that's one reason why it's so useful for parsing, because if you get back a nothing on one side, it can still, parse whatever you've got on the other side, right? So we have these monoids all over Haskell, and the type system itself is monoidal. And knowing this and finding it to be such a pervasive pattern throughout Haskell, throughout logic, throughout mathematics, has been a really profound and exciting experience for me. Unfortunately, I like this kind of thing better than I like actual software engineering. All right, so we will close with this from, again, Sir Thomas More. The ordinary acts we practice every day at home are of more importance to the soul than their simplicity might suggest. I've chosen this one because to me this is what monoids are. Monoids seem very simple. They're very simple things, and we see them everywhere. But these ordinary, simple things are much more important to our soul, to the soul of Haskell, to the soul of mathematics, than their simplicity would suggest. And I'm going to stop there before I fall down. Okay, so here is, that should be a link to the talk. And there is another, this blog post is another sort of take on the evolution of monoids, and is really good, so I really recommend it for follow-up reading, should you be interested. Okay, I'm done. One time I gave a talk at a conference, and after I got done speaking and it was time for questions, everybody just stared at me, and then one guy raised his hand and said, "I don't think any of us have any idea what you just said." So, but I'm hoping that there aren't very many questions because everything was just completely clear. Yes?
Thank you very much for that talk. It was very clear indeed. I like how you categorize things like additive intersection into sort of disjunction type things and multiplicative union to conjunctive type things. I don't know if you've looked into adjunctions and how additive and disjunction is actually left adjoint stuff and multiplicative and conjunctive is right adjoint stuff. And I also like your observation that some of these things feel more forgiving than the other ones. And I think the more forgiving ones are the right adjoint ones, because there's this good old slogan in category theory that says that right adjoints preserve limits. And I think the limits are the things that are kind of nice for us. Have you given any thought to that aspect?
Well, I've just been learning about adjunctions recently. So like I said, I'm kind of a novice with category theory. But yeah, I like that observation a lot. I think that's, yeah. I like when, what I've been loving about finally learning some category theory, is that it seems to validate so many of my intuitions. Category theory is self-help.
Is there anyone else?
So I hadn't realized that is it true that there's always a conjunctive version and a disjunctive version for, say, Haskell type, for each Haskell type, where you can have one if there is there also the other?
I always hesitate to say that something is always true. It has been true for every type I've tried to do it with so far, but so I don't know if maybe somebody who knows much more about this might have a different answer, but it has been true of every type I've tried to do it with so far. It's just some of them, like I said, don't seem particularly useful, but you can make them, and they behave the way they're supposed to.
Okay, thank you.
So I was just wondering, with your work on this and working on the book, have you found that when you're talking to people without a background in category theory or Haskell, maybe more general software engineers, if you're explaining about monoids and the benefits of there, has there been a particular approach that you found useful to kind of try and convince people who maybe are worried that they haven't done maths for so long, they're not good at maths, how are they going to use this complex algebraic structure? Is there a really succinct way that you found to kind of convince people of the value of this?
That's a really good question and a difficult question. I usually do with, so I've been teaching Haskell, for example, at a meetup I taught it for about a year before I moved out of Austin. And most of my students there were programmers from other languages. I mean, it's fairly rare that I meet someone who learns Haskell as their first programming language, but so they were programmers, from Java and JavaScript and C#. And going through this progression, sort of what I did just now, and then convincing them that having a word to be able to talk about this thing that we just find everywhere, right? That we can kind of unify all these things into one into one way of thinking about it seems to have been the best thing that I've found so far. That's less exciting for some people than it is for others, but that seems to be the thing that has worked best. Like, you know this pattern. You've seen it all over the place. I know you have. So let's just be able to talk about it. Identify it when we see it.
Is there anybody else?
Yeah, I like to say that jargon is like information compression, right? Once we have a word, monoid, it's like we've compressed all of this knowledge and all of this intuition into just one label that we can kind of conveniently reference whenever we need to.
I have just one comment, maybe a small question. That you took as an example for monoid disjunct sum for sets. And you said that it's actually easier to than the normal sum. Maybe the reason is actually that this disjunct sum gives you a free monoid rather than a monoid with some equations inside.
Yeah. Yes. Sorry, I don't have anything to add really, but yes.
Is there anybody else with a question? All right, well, thank you very much.
Okay, thank you.